Right. Well, welcome everyone to our final quarterly webinar of the year. So this is the SXP-SIG. We host our quarterly webinars, and today I'm excited for this webinar that's co-hosted by our MBMA Sub-SIG. And the webinar will be handling missing covariates in model-based meta-analysis, use case for competitive benchmarking. And our speakers today are Monica Simeone, Rana Reich, and Phyllis Chan. And we're really excited for them to be sharing some of their good work today. So as is the process for our webinars, I'd like to, if anyone's interested in joining our special interest group, please follow this, either go to our website, send us an email, or follow this QR code. It's free to join. We absolutely do not overwhelm anyone with our emails. They're usually an average of once a month that we're sending out a bulk email. And if you're to go to our website, you see we have a lot of good information about statistics and pharmacometrics, as well as a summary of all our past events and webinars that you can follow up on. And this one, will also be posted to our YouTube account afterwards, but I definitely would encourage everyone to join if they haven't yet. And it's free to join. You don't need to be a member of ASA or ISoP. So please go check out our website. And even if you have joined, it's always good to see what the updates are on our website. So with that, I will pass it over to Monica Simeone, who's the co-chair of the MBMA Sub-SIG, who will share some information about the Sub-SIG and MBMA.
Thank you, Luke. For people that are not familiar with MBMA, model-based meta-analysis is a method to integrate data from multiple studies using mathematical models to quantitatively describe the effect of treatment time and patient population characteristics on the trial outcomes. Data are coming from clinical trial results and can be summary level data in the public domain and or proprietary data. This modeling approach helps to answer important questions in clinical development, like the one listed here, like quantify the therapeutic landscape, simulate head-to-head comparisons, optimize clinical design, predict long-term outcomes based on the short-term ones, guide dose selection for unstudied indication or population, and last but not least, to quantify the effect of covariates on treatment response. And one of the topics that we discuss within our special interest subgroup is in fact how to handle missing covariates. We organized this discussion within the team, of which the two speakers of today, Phyllis Chan and Rana Reich, are part of. Here you can see our email. You can find more information in the website, and we have also a LinkedIn account. So please reach out to us. As I said, today we have two excellent speakers, part of our team, and are Phyllis Chan. Phyllis is a pharmacometrician in the clinical pharmacology modeling and simulation group at Genentech. Before joining Genentech in 2017, Phyllis worked at BMS, obtained her PhD in pharmaceutical sciences from Auburn University, and was a postdoctoral fellow at the USC Biomedical Simulation Resource. She specializes in population PK, exposure response, and tumor growth inhibition overall survival analysis. She will introduce the case study and will be followed by Rana Reich, who works in the data and data sciences group at Sanofi. Rana is an associate director in clinical modeling who joined Sanofi since 2020. She has a PhD in applied mathematics and statistics from Paris-Saclay University. Her current work involves providing modeling and simulation support to guide internal decision-making, optimize drug development by leveraging different sources of data, real-world data, historical clinical trials, etc. So I'm sure you will enjoy this talk. And with that, I leave the stage to Phyllis, and please put your question in the Q&A Zoom chat, and will be answered at the end of the presentation. Thank you.
Thanks, Monica, for the introduction. So next slide, please. First, I will present a case study where it incorporates some of the most common uses of MBMA to support model-informed drug development. And I will illustrate that missing covariate data is ubiquitous in MBMA. Therefore, there must be a plan in place on how to handle them during the analysis. So fenebrutinib is a BTK inhibitor, and it was designed to block B-cell proliferation. And it was investigated in a study in patients with rheumatoid arthritis called, the study is called GA29350. In this study, there are two cohorts of patients. One cohort of patients had an adequate response to methotrexate, and the other cohort of patients had an adequate response to TNF inhibitors. And for all patients on the study, they continued with background methotrexate therapy during the study. Next slide, please. For the patients who had an adequate response to methotrexate in this study, they were randomized into one of the 5 treatment arms. One is a placebo arm, and we also had 3 arms of fenebrutinib, ranging from 50 milligrams once daily to 200 milligrams twice daily. And there was also an active treatment arm using adalimumab, which is one of the standards of care for the treatment of rheumatoid arthritis. For the smaller group of patients who had an adequate response to TNF inhibitors, they were randomized into 2 treatment arms, either the placebo arm or the fenebrutinib high-dose arm, which was 200 milligrams twice daily. And I also want to mention that the TNF inhibitor, patients who had an adequate response to TNF inhibitors, they were classified as harder to treat patients. For this study, the primary efficacy endpoint was ACR50, which is whether or not the patient had achieved 50% improvement threshold. So this is a binary variable at the individual level, either yes or no, but at the aggregate level, it is the proportion of patients of achieving 50% improvement threshold. And a key secondary endpoint for this study was DAS28. And both DAS28 and ACR50 were measured at multiple time points during the study. Therefore, there is longitudinal data for both ACR50 and DAS28 for this study. Next slide, please. So in order to fully understand the treatment effect of fenebrutinib, a combination of population PK, exposure response, and MBMA were conducted and to fully utilize the data available. And also, we wanted to look at the data from different approaches. So specifically for MBMA, the objectives were to develop a model based on aggregate level data, and also data from GA29350 as well as from publicly available literature data. And we were also interested in investigating the covariate effects, in particular, the covariate effects on the treatment effect between patients who had an adequate response to methotrexate compared to patients who had an adequate response to TNF inhibitors. And ultimately, we wanted to confirm the placebo and adalimumab response in GA29350 compared to publicly available data. And we wanted to make an indirect comparison between fenebrutinib and tofacitinib. Tofacitinib is a JAK inhibitor and is another standard of care for the treatment of rheumatoid arthritis. And we want to make this comparison for benchmarking efficacy between fenebrutinib and tofacitinib, even though tofacitinib was not investigated and used in GA29350. Next slide, please. So before doing the MBMA, we put together a database through systematic review, and this collected the data from literature published between 2012 and 2017. And this database was combined with an existing MBMA database that was constructed in 2012, therefore covering the publication prior to 2012. Next slide, please. And in this database, not all publications reported all statistical variables of interest. So for example, one publication might only have the standard deviation, and then the other publication might only have the confidence interval. Therefore, calculations had to be made to standardize the variables, and then also to derive the missing statistical variable. Other data that needed to be standardized included units for endpoints, for the covariates, and also for the doses of the different treatments. And for this analysis, the covariates were pre-specified, and they were the common and well-known covariates for rheumatoid arthritis. And not all the covariates of interest were reported in all of the publications. So the missing covariate values needed to be imputed. And for this analysis, a multivariate linear regression was used to impute missing covariate values. And later in the presentation, Rana will go over some of the different options that are available to impute the missing values. So now we have an augmented MBMA database that was standardized through imputation and derivation. Then we wanted to explore the database to see the extent of the data available. And through this exploration, we found out that ACR 20, 50, and 70 were the most prevalent efficacy endpoints in this database. And therefore, these three endpoints were used for the subsequent MBMA. Next slide, please. And in this MBMA database, it contained 62 citations, and there were 4 treatments of interest, mostly from placebo, adalimumab, tofacitinib, and fenebrutinib. And of these treatments included in the database, they were between 1 and 6 dose levels, and they were between 1 and 47 time points across the treatment arms. And I want to mention that from GA 29350, the data was incorporated as aggregate level data, not as individual level data. Next slide, please. For the MBMA itself, a hierarchical regression model was used to simultaneously fit ACR 20, 50, and 70 longitudinal data. And this ensures that the proportion of ACR 20, 50, and 70 is estimated in the correct order. And the longitudinal treatment effect of time was described using an exponential function, which means that there is an increase in treatment effect over time to a maximal level. And of the covariates of interest that were tested, there were 3 that were statistically significant. And the 3 were whether or not the trial had 80% or higher of patients who had inadequate response to TNF inhibitors, and the proportion of patients who had inadequate response to methotrexate. And the last significant covariate was whether or not the patients were on background methotrexate therapy. The different dose response relationships of the treatments incorporated into this model were described using Emax, linear, or single level relationship, depending on the availability of the data. And model evaluation was conducted comparing observed versus predicted values. And we used the final MBA model to simulate the longitudinal treatment effects, both for fenebrutinib at various dose levels, as well as the simulations for the other treatments of interest were performed. And this allowed a direct and indirect comparison of fenebrutinib with the treatments of interest. Next slide, please. So here first, I will show you the model evaluation and showing that there is a good model performance and a good agreement between the observed data and the model predictions. First here shown as placebo response. And on the left and center panels, we have the model evaluation for the patients who had an adequate response to methotrexate. And on the right are the plots for patients who had an adequate response to TNF inhibitors. And the plots are stratified by ACR 20, 50, or 70. And in these plots, the black circles are the observed data from the various publications and from GA29350. From the publications. And then the vertical lines are the 90% confidence intervals. The blue curves are the median of the prediction, and the shaded gray areas are the 90% prediction intervals. And in some of the panels, you see that there are green circles, and these are the observed data from GA29350. So from these plots, you see that there is it shows a good model performance because there is a good similarity between the observed data and model prediction overall from the various publications and the placebo response. And also because there is a overall good consistency between the black circle and model prediction and the green circles from GA29350 indicates that the data from placebo data from GA29350 is consistent with historical data. Next slide, please. And next, I also want to show the model evaluation for patients who had received adalimumab on the left, and also for the other active treatments on the right. And I want to point out that on the top left for ACR 20, you see that there is a overperformance of patients in GA29350 in green compared to historical data. However, for ACR 50 and 70 on the left, center, and bottom, there is a good consistency of adalimumab data from GA29350 compared to historical data. Next slide, please. So lastly, we use the final model from the MBMA to simulate the longitudinal treatment effect of fenebrutinib at various doses. And here I'm showing only for the highest dose investigated, which was 200 milligrams twice daily. And this was compared with the model predicted performance of efficacy of adalimumab and tofacitinib. And based on these simulations, it shows that the highest dose of fenebrutinib would perform similarly compared to adalimumab and tofacitinib for both patients who had an adequate response to methotrexate, as well as for patients who had an adequate response to TNF inhibitors. So because these simulations failed to show that fenebrutinib would have a superior efficacy response compared to adalimumab or tofacitinib, ultimately the team used this data to make the decision to terminate the investigation of fenebrutinib in patients with rheumatoid arthritis. So next slide. So I've just showed you a case study where it incorporated the and confirmed the comparison of placebo and adalimumab data of the in-house study to historical data. And also we did a indirect comparison and benchmark efficacy of fenebrutinib to the tofacitinib, which is one of the standards of care for rheumatoid arthritis, but was not used in the study of GA29350. And I hope that I have convinced you that missing covariate data will be encountered more than likely during an MBMA, and therefore how to handle missing covariate data should be part of your analysis plan. So next, I will hand it over to Rana, who will go over some of the different types of missing covariate data, as well as the different options and how to handle them during the analysis.
So thank you, Phyllis, and hello, everyone. So in the second part of the presentation, I will tackle more technical and methodological aspects of statistical approaches that are used to handle missing values in meta-analysis. So missingness is a major and a common problem in meta-analysis, and it may lead to several issues, such as biased estimates, reduce the power of the meta-analysis, overestimation of the effect size, as well inconsistent results. Particularly, I will talk about this issue in the framework of meta-regression. And before digging into the details of the statistical approaches, I would like to introduce you what is meta-regression. So meta-regression is a powerful tool that helps you to synthesize information from multiple studies that investigate the same research question. It's a statistical approach that analyze the relationship between a dependent variable called as well the outcome. It will be the outcome of the study and link it to one or more of covariate or potential modifier. Of course, the outcome may not be completely explained by this effect modifier. That's why we can add like a study-level random effect to express the heterogeneity between the study, as well as a sampling error. And as you can see, both study-level random effect and sampling error are follow a normal distribution centered at 0. For the level random effect study, we can see that more the variance to 2 is high, more the heterogeneity between the study will be important. Meta-regression is used and have several applications to support clinical trial development. For example, it can be used to link short-term endpoint and biomarker to predict long-term endpoint. Furthermore, it's important to understand the kind of information that may be missing in historical clinical trials. First, we can mention missing value at level of outcome measure. This can due to patient dropout from clinical study that may happen for several reasons, adverse event, loss of follow-up. We may have as well missing value at level of baseline summary characteristics, because not all studies are supposed to report the same set of baseline characteristics. And finally, we may have missing value at level of sampling variance. For example, the variance of progression-free survival hazard ratio that could be reported in one studies and not on other. Today, I will focus particularly on the statistical approach that are used to handle missing value at level of covariates, especially that Tipton and Al publication found that 45% of meta-analysis that they reviewed reported the problem with missing covariates. So before applying the statistical approach, it's important to understand the missingness mechanism. And here we can talk first about missing value that are completely at random. And here the probability of missing data will be unrelated to any other variable. and as well unrelated to the variable where we have missing itself. A good example is to consider missing data that may due to the responses to a survey, to a research survey, for example, about depression that are lost in the mail. Next, we may have missing data at random, and here we have the probability of the missing data of this variable related to other measured variable, but not related to the variable where we have missing itself. And as an example, we may have missing value because, let's say, males are less likely to respond to a depression survey. And here we can see that the missing value depends on the gender of respondents. And things may get more complicated when we have missing value not at random. And here the missing value of variable are related to the variable where we have the missing itself. And as an example, for example, respondents may fail to fill the survey due to their level of depression. So by recognizing the difference between the three types of missing value, it is very important to choose the suitable statistical approach and ensure accurate and reliable analysis. Furthermore, it's important to continue exploring and understanding missing baseline characteristics. So this can be done by investigating the percentage of missing value in each covariates in order to identify which covariates has the most significant amount of missing value and where we should put more effort to understand them as they require more attention. What we can do is to provide a plot where we have the percentage of missing value for each of the covariate. And here we can see clearly that we have source and factor and date of infection are the covariate that refers more missing values. Another important point is to check if the missing value has a specific pattern or distribution. Are missing value concentrated on some group of the study or are evenly distributed across the studies? And here we can provide a plot as plot 2, where we have the missing data in black for each of the covariates and across all the studies, so we can recognize the presence or not of some specific patterns. Furthermore, it's good to investigate if the likelihood of missing value in a variable are related to other measured variable. And this can be done by provided a matrix plot which can be based on Pearson or Spearman coefficient correlation and help us to identify what are the variables that are highly correlated between them. And lastly, it's important to investigate the relationship of effect size and the missingness in the covariate. So here in plot 4, we can have the distribution of effect size among the missing and non-missing value in a covariate. And when the distribution, as in panel A, are consistent, this is good compared to the panel B, where we can see a difference in the distribution between a missing and non-missing value. And this can lead to a biased estimates. Let's move right now to what a statistical approach are used to handle missing covariates, and I will start by the ad hoc approaches that are widely used in meta-regression. So first, we have the complete case or list-wide deletion approach. It requires to delete all the study where with any missing values. So this approach may seem straightforward, but it can lead to a significant loss of information, which can lead to misleading conclusions. Furthermore, these methods assume that the data are missing at random, which cannot be always true. And when the data are not missing at random, this approach can lead to a biased estimates. As a second approach, we have shifted case analysis or pairwise deletion. This method consists to delete only a specific variable having missing value while continuing to analyze the other covariate without missing values. Of course, this method has the advantage compared to the complete case analysis that it reduced the loss, let's say, of information. However, different data sets and variable will be used for each meta-regression model estimated, and we should pay careful attention on what covariate we want to delete, especially if this covariate is highly correlated with other measured variable. And lastly, we have the single imputation that requires to replace the missing value by the mean or the median if the covariate is numerical, or by the most frequent category if the covariate is categorical. Single imputation may outperform the listwise and pairwise approaches, especially if we have a few values that are missing. However, it does not take into account of the correlation between the variable, which may lead to an underestimation of the variance of effect size. And nevertheless, Tipton and al. Showed that 86% of meta-analysis use ad hoc approaches to handle a missing covariates problem. I will move now to introduce you more advanced and robust technique that are used to input missing values called multiple imputation methods by chained equation, or MICE for short. So MICE, it's an iterative procedure that impute missing value through a series of predictive models. So the process will start by replacing the missing value by a temporary placeholder. This can be done by using simple algorithm like replacing the missing value by the mean or the median, or a random selection from the non-missing values. As an example, as you can see here, we have 3 covariate A, B, C, and the missing value are highlighted in red. And we can see that they impute the missing value by randomly selecting across the non-missing value in each covariate. Next, we should set back to missing the placeholder on a specific covariate, let's say A, and regress A based on the remaining covariates, which are in our case B and C, using a regression linear model. And after, the fitted regression model will be used to predict the missing value in covariate A. As you can see, this process can be repeated separately for each of the remaining covariate, namely B and C. For example, we may start from the beginning to replace the placeholder in the covariate A by the predicted value that we obtained through our fitted regression, and repeat the same process for B and C. So MICE result multiple imputated data sets. And this is the beauty of the MICE, that we can do the analysis separately on each imputed data set, and then the final model will be obtained by pooling or combining the results from the different analysis. So it takes into account, as you can see, of the variability around the imputed data set. If you are an software user, you can use MICE and metaphor packages to perform MICE. And I would like as well to highlight that MICE have some key assumptions. So it assumes that the missing data are missing at random, the linear relationship between the variable, as well as the missingness should be ignorable, which means that the distribution of effect size should be consistent between missing and non-missing data for each of the covariates. However, as you know, the variable may not be always linearly linked. So as an alternative, we can use the multiple imputation based this time on the random forest. So what is random forest? Random forest is a supervised machine learning technique that provides multiple decision trees, and each tree will be built based on a subset of random feature and a subset of data, and the final result will be obtained by aggregating results from a different tree. So here, each node in the tree could be seen as a decision rule on a specific covariate. For example, we will split the data according if the age is higher than 80. So, or the observation that respects this condition will move to this node, while the other will be classified in this node. And the leaf node of the tree will be the class or the value that we want to predict. To better understand how multiple imputation using random forests work, we can consider this example where we have two covariates, the score and the age. As you can see, we have missing value at level of age. So what we want is to predict the missing value for age. So the age will be the leaf node of the tree. But first, we will start by imputing missing value by the mean, and then we will tag each observation as training or predict. So the predict will be to the observation where we want to predict missing value. We will train the random forest on both training and predict, and after the fitted random forest will be used to predict the missing value of age. The advantage of random forests is that it is flexible, so it can handle both numerical and categorical covariates. It's robust because it's less sensitive to the presence of outliers. However, it becomes computationally expensive when the number of predictor or and observation increases. So let me now show you and compare the performance of all these statistical methodology, considering a first set of simulation study published in Diaz et al. In 2021. So it was based on Bangert-Drown's data set that refers 43 studies. So here the studies are a school, where the sample size range from 16 to 542 students. And this meta-analysis aimed to assess the impact of providing feedback on the improvement of student learning outcome. And we have four covariates: the imaginative component, the informational component, the personal component, and the meta-cognitive reflection. So Diaz will base the simulation on the complete data, which will serve as a baseline reference. And they will create missing values to build the incomplete data set with respect to the different missingness mechanism. So missing completely at random, missing at random, and non-missing at random. And within each panel, they generated the 10,000 incomplete data set with different proportion of missing value ranging from 10 to 50%. So here you have the results of simulation that compare complete case versus multiple imputation methods, considering the missingness in one covariate. So in the plot at the left, you have the bias of the estimated coefficient slope for this covariate. Each panel represents a different missingness mechanism. We have here missing completely at random, missing at random, missing not at random. And within each panel, we have the bias of the estimated coefficient as a function of the proportion missingness. And each color refers to different statistical approach. So in red, we have the complete case. In green, we have the multiple imputation by default. It is based on a regression model, and we have multiple imputation based on a random forest in blue. Overall, we can see that the bias of the estimated coefficient will increases when the proportion of missingness increases. And as expected, when the data are missing completely at random, the difference of bias is ignorable between the three methods, especially when the proportion of missingness is less than 40%. When the data are missing at random, we can see clearly that the multiple imputation by default outperform the other approaches, even when the data are not missing at random. At right, we have the estimated standard error for the three approaches. We can see as well that the estimated standard error will increase when the proportion of missingness increases. However, we see clearly that for multiple imputation methods, both by default and random forest, we have a precise estimation of standard error, while for complete case analysis, it consistently overestimates a standard error. So to recap, the simulation results shows that multiple imputation outperform ad hoc approaches. I will show you as well another simulation set, which was published in Lee et al. Publication in 2022. So for the complete data generation, that always serves as a baseline to compare the performance of the methods after data imputation. They will be generated based on the meta-regression model. So as you can see, they generated sampling error from a normal distribution centered at 0 and with a variance of 1. They considered different simulation scenario. For example, they considered the number of study of 20, 50, and 100. And for the between study heterogeneity standard error tau, it was set to 0, 0, 0. It means that there is no heterogeneity between study, 0.10 and 0.4. For X, the number of covariates, they considered 3 covariates that were simulated from normal distribution centered at 0 and with a variance of 1. They set the intercept value to 0.10. And for beta, the slope coefficient, it was set to 0, 0.05, and 0.2. And thus they are able to simulate the outcome of the study. Of course, we need to create incomplete data generation and create a missing value. So they did that by assuming the MAR mechanism and considering two different proportion of missing value, 20% and 50%. For the simulation results, they compare ad hoc approaches versus multiple imputation. So here you can see the relative parameter bias of the slope of the 3 covariates. That's why we have a box plot. In each panel, for example, in these 2 panels, we have tau equal to 0, which means that they do not consider, they consider that the study are homogeneous, while here tau was set to 0.4, so we have a more important heterogeneity between study, and we have different proportion of missingness that vary between 0.2 and 0.5. In this first panel, they considered 20 simulated data set, while here they considered 100 simulated studies, let's say. Overall, we can see clearly that multiple imputation has the best relative parameter bias compared to the ad hoc approaches. However, of course, this bias may increases when the percentage of missing value increases or when the heterogeneity of between study are high. We can see as well that the complete case analysis and the shifted case analysis lead to biased slope coefficient, but in the opposite direction. But overall, this simulation set as well showed that multiple imputation outperform ad hoc approaches. So to recap, I show you today that missingness is a serious problem that we may have in meta-analysis, especially at level of covariates. Before applying the statistical approach, it's good to understand the missingness mechanisms and the correlation between the variable in order to choose the suitable statistical approach to apply. And comparing to the ad hoc approaches that are widely used, we show you today that it's better to apply multiple imputation. It take into account of the variability and lead to better results. But of course, this technique will be less performant when we have a high proportion of missing value or when we have some assumption violated. So here references that we use for this presentation, and I would like to thank you for your attention, and we welcome any question or comment you may have.
Thank you, Phyllis and Rana, for the excellent presentation. Very, very interesting. There are already some questions on the chat. And the first one was for Phyllis. And Phyllis, can you elaborate how the correlation of the 3 endpoints are incorporated in the MBMA? Have you evaluated the difference with or without the imputing the covariates?
The three endpoints used for the fenebrutinib example were ACR 20, 50, and 70. And that means that it's whether or not the patients had achieved 20%, 50%, or 70% improvement threshold. And there's an assumption, unless there's a data recording error, that if a patient, for example, had achieved ACR 70, then definitely that patient had also achieved ACR 20 and 50. So the order of the data, whether or not it is observed or predicted, needs to be that the ACR 20 needs to have the highest value compared to ACR 50 and 70. And of course, ACR 70 should have the lowest proportion. So in order to make sure that this order is maintained in the model itself, we incorporate them simultaneously, and then there's an additive estimation so that in the model prediction, ACR 20 would be highest compared to ACR 50 and 70. And then the second
was, have you evaluated the difference with or without without imputing the covariates?
We did not. So we only imputed for the missing value. We did not test the sensitivity analysis where we did not impute.
Okay, thank you. And the second is still for Phyllis. Phyllis, could you please elaborate on efficacy benchmarking based on direct versus indirect comparison?
So I assume this is regarding efficacy benchmarking in general, not just about fenebrutinib. So for drug comparison, I think this could be done for any type of meta-analysis, not just MBMA. So this is when you do have data evidence available. For example, from a head-to-head trial, you randomize between two treatment arms, so you can make this comparison directly. And then for the indirect comparison, this is where the strength of network meta-analysis or MBMA comes in. So for example, if you have a trial data, historical data, maybe even where you have you compare treatment A compared to treatment B, you have this observed data available, and then you have a second trial where you comparing treatment A compared to treatment C. But then you want to compare the efficacy between treatment B to treatment C. So you don't have this direct comparison. You want to make this indirect comparison, like we did in our fenebrutinib example, where we have data between fenebrutinib and adalimumab, but then we don't have data comparing fenebrutinib to tofacitinib. So we want to make this indirect comparison. And if without meta-analysis, if it's without doing any model, then there's a lot of assumptions you have to make to do this indirect comparison. For example, you have to make sure that the patient population are similar between the two trials, and also the general study design have to be similar. But then if you have a model through MBMA, for example, if there's some difference between the patient population, you could adjust them through a covariate and incorporate that into the model. So then you can make this indirect comparison and incorporate more comprehensive data into your analysis, more evidence to confirm whether or not these two treatments are comparable. I hope that answers your question.
Thank you. And the next question is for Rana. Does random forest have a higher bias in MNAR case? Why is that?
Not necessarily. Because the multiple imputation, even using random of forest, assume that the data are missing at random. The bias will increase when the data are not missing at random. Here, where we can have like the performance of this technique decreases. But multiple imputation in general, if it was based on regression or a random forest, one assumption is that the data are missing at random.
Okay, thank you. And another question for individual study, what methods would be considered most appropriate to impute for missing covariates, continuous versus categorical variables? Any good reference?
It's true that here it was like for summary study, but for individual, I think this same technique can be used. The key message here is really to use multiple imputation versus the ad hoc approaches. So both multiple imputation based regression or random forest, but it's true, it's important to do all this exploratory exercise to understand the correlation between variable. If it's not linear, we should go with multiple imputation using random forest, for example. So it could be used at level of individual or summary study.
Okay, thank you. Another question still for Rana. You said that there is an assumption of linear relationship in multiple imputation method using MISE, if I am not mistaken. If I understand correctly, MISE is a collection of methods, not only one method. So does your statement hold true for all methods in MISE? I refer to the assumptions.
It's not clear to me. It's through multiple imputation, the concept how it work is the same, because it will provide like multiple imputed data set, and the final results should be leveraged across all these, the analysis done separately on each imputed data set. Of course, if the outcome is continuous, we will do if the variable, let's say it's numerical, we will do like regression. If we are sure according to visualization plots that the variable are linearly correlated. If the variable is binary, in this case, we should do logistic regression model. So yes, the model could be different. It could be regression, logistic. When it is not linear, we use random forest, but the concept is the same of multiple imputation.
Okay, thank you. And another question is for the multiple imputation for covariates A, B, and C. What if two missing covariates are highly correlated, for example, body weight and BMI? Should we just predict and use one covariate in the model instead of two?
It's true that multiple imputation performance may decreases in case of presence of multicollinearity. So maybe yes, instead of using two, we will use one of the two covariates. And after all, if we have always this question, we can do sensitivity analysis, use one, two, impute, do cross-validation, and check the prediction and decide. But usually, if we have multicollinearity, it's better to use one of the variable.
Thank you. And yes, one key question is there a percentage of missing data above which it is not reasonable to impute?
Yeah, it's true. There is not a common threshold. When we have like 5 to 10, this is a reliable, let's say, a percentage of missing value. However, I think this technique may handle from 30 to 50%. Having more than 50%, it will be like, it will have an effect on the performance of imputation methods. Yeah, and all this depend as well on the analysis, what are our purpose for the analysis, and it's always important to have clinical insight to see if it's very important to consider it or if we can like not imputed because of this high amount of missing value.
Okay, thank you. Another question is for, yeah, I have a question regarding missing data value of an adverse event percentage. If the dropout rate is high and about 10% of dropout related to that adverse event, the data value in the later time points appear 0%, but oh wow, but the total N of subject is low due to the dropout. How should we handle these kind of missing values? I mean, I think that
But I didn't understand clearly if is it 10% of missing value that, but he has a low number of observation. It's true that here what we may have that the multiple imputation performance will be not be stable. Of course, multiple imputation is better than replacing by mean, median, or the average, but due to the small observation, the performance will be not stable.
okay, thanks. And just, I think, yeah, there was an initial question about, can you compare and contrast the imputation of covariates via multivariate linear regression with empirical spline models? I think it's for both, I think, the question.
I think, yes, we can consider like different link, logistic, regression by spline, but the concept of multiple imputation remains the same of creating and taking into account variability by creating many realization of imputed data sets.
Thank you. And I think we are at the hour, so I think, yes, for the other question will be answered online. And yeah, thank you very much for our today presenter. The presentation were really, really interesting. And yeah, I will invite you to follow us for the next here webinars. I don't know if Luca and any of the organizers want to add anything to this.
Just thank you very much for the great presentation. And we do plan on having our next webinar, I believe in March. That's what we're timing. And if anyone has any topics they would like to give as a webinar, just please reach out to us, send us an email. And yeah, thank you very much everyone for attending.